Welcome to today's webinar. Whether you are a long-time DC fan or just starting to get to know DC, we are excited to have you here today. Welcome to Unlocking Direct Current, Immediate Savings, Immediate Energy Access. What a program. We're thrilled to have you join us today. And our hosts are Dr. Stephan Rupp, who is Product Manager at Maschinen Rheinhausen. And we also have Mame-Thiedel, Thiongane, and Romain, Scolan, Project Manager from Cégélec, VINCI Energies. So these people are valued partners of CurrentOS, and they are going to be our hosts today for this webinar. We are also with Prashant Kurup, who is General Secretary of CurrentOS. And I am Raphaël Raymond. I am responsible for marketing activities at CurrentOS. Before we dive in the content, I have a few housekeeping notes for you. We are going to present for approximately half an hour our content, and then we ask you to ask any question in the chat. We have set aside plenty of time to answer to all your questions after the presentation and have a discussion. This webinar is being recorded, as you know, so if you would like to turn on your camera and your microphone, it's all the best for us because we can see you when you ask questions, and we are a very interactive session. And following this, if you want to see what's going on with CurrentOS, go to LinkedIn. Sorry, it's a great way to stay connected with our vibrant DC community. We have now almost 4,000 followers on LinkedIn, so you can see a lot of DC news on our LinkedIn page. And so without further ado, Mame-Thiedel, Romain, and Stephan, over to you.
Well, hello everyone. What is CurrentOS? So CurrentOS is a non-profit organization with a goal to define the standard in direct current distribution. What is important to know, actually, there is no standard for the direct current distribution in a building or in an infrastructure. So we can do what you want. So CurrentOS is an organization with want to define the standard for the distribution of direct current. So with this standard that make all the rules you have to respect to make a DC installation. So actually we are more than 70 partners, different companies, industry, university, organism of certification. So and we work in different countries, North of America, Europe, and Asia. So, Raphael, you can change the slide, yes?
Yes.
So, on this side, you can see different newspapers which speak about the power consumption. So, what we can see actually in our countries is that the AC network, so the alternating network, is saturated or will be saturated. For example, in France, the demand of electricity will increase, and we know that the difference between today's and in 10 years, so in 2035, the demand of electricity will increase of 40%. So it's huge, and actually we are no solution to make the solution for this increase of demand. So DC network is a solution to reduce the waste on the AC network.
Yeah, and this is a look about the future. So congestion is an issue today. Will it become any better? If you have a look at the energy transition on a global scale, it means that the power grids will need to transport 2.5 times the amount of energy that they're transporting today. So power grids are growing by a factor of 2.5. And what's most important, the connectivity we need for renewables will grow by a factor of 10 starting from today. And this is what you see here on that slide. And it's renewables on every voltage level. So starting from the high voltage DC, there are offshore wind farms, to medium and high voltage level with wind farms then hydrogen storage with electrolysis, fuel cells and batteries. And on the low voltage level, we see bigger PV installations with their batteries, charging stations and factory automation. And all of the renewables have one thing in common. They are DC systems. So when we connect them as today individually on the AC grid, we need a lot of connectivity, and this is creating the congestion. So as Romain has put out already, DC is a way to reduce the congestion on power grids and to discharge the grid out of a lot of renewables. The focus of today is the circle below, low voltage DC systems. And I'm going to show you on a couple of slides what's happening in the future. Today, if you please change to the next slide, we are looking for compatible solutions. That's essentially what integrators say. DC is something that we all would like to install, but it's a difficult type of project because everything needs to be designed on a project basis. What we need is compatible products. And I can show you on the next slide what it means in practice. When we are building installations today, so we are starting from yesterday's worlds with purely AC systems, and then in the middle part of the figure, you see a lot of DC installations are now being added on the grid, but all of them are converted into AC. So you have a lot of systems to connect over power converters in a hybrid network. And this is the situation that generates the difficulties. This is the reason for the stress on the power grids and the congestions we are facing. If you please move to the next slide. What we are proposing instead of that are DC microgrids at the edge of AC. So now in the middle of the system, you see a DC grid, and all the DC systems like large PV installations here on the roof of the building, battery storage, charging stations and factory automation now connect over a DC grid. But what's missing today are the standards for the DC systems. So how do I get a PV panel that I connect over DC to the battery? How do I get machines matching that DC standard? And this is in fact what Current OS is trying to do. So the next slide will show you a couple of applications. So we are talking about DC in buildings, DC in truck depots or like logistic depots in the middle. Then we have solar parking lots, transport systems, public lightings. And just carry on to the next slide. And what we will see in the future is something we call DC stations, which is basically the same thing as a transformer station, but now the output is low voltage DC, for example, on a 700 volts level. If you animate the rest, please, then we are targeting at connecting the devices on a DC grid. So here you see the systems again, and now we have a DC grid in the middle. And this is what we are setting up. And this figure is taken from a research project that the unpronounceable Maschinenfabrik Rheinhausen is undertaking with a couple of partners. And this will be based on Current OS. So to get back to Current OS.
Yes. So here you can see different projects in direct current, which are realized by the different partners of Current OS. So you can see also the partnership with Shift2DC, which is a new European project for 4 demonstrators in building, in logistic, in industry. So we need actually more projects in DC. The objective of the demonstrator of this project is to show the benefit of direct current. And today we will speak to you of the different benefits of the distribution in direct current between an alternating current distribution. So we will speak about two demonstrators, two examples, one in Lille in the north of France and the other one in Berlin in Germany. So for the first one, the first demonstrator in France was realized by Cégélec, companies of VINCI Energies.
So hello everyone. To talk about the projects we did, which we named the Wave Lille, which is the first demonstrator in France. So a year ago we completed our first DC installation, which is represented by the synoptic below. The system is with the system we power different spaces like a meeting room, 5 decks, 5 offices, and a coffee room. The system is powered by a 50 peak kilowatt photovoltaic production, 12 kilowatt hours battery storage, and an NADIS support, which is the France networks, the France network system. With this installation, we powered directly on DC the electrical systems where we replace the usual AC sockets by DC chargers, which are in USB-C, which is the standard in DC. If you look at the synoptic, you can see that we have, as I said, 3 different energy sources which enable the system to work continuously even in challenging conditions. And in this system, you can see that we delayed all the different conversion stages that, as Stephan explained, are the source of different energy losses. You can move to the next slide. So here you can see the different materials that we installed. In this in the building we have 2 different buses of 2 different voltage levels. 2 different voltage levels with the white outlets. We have a 350 volt level, and with these USB-C chargers we have a 48 volt voltage level. Here are the batteries that we installed, and this is the DC cabinet where we have all the electrical devices that we need to power the system. You can move to the next slide. So here you can see the different benefits of this installation. So with the installation, we've seen that we have 20% less energy that is consumed, which comes, as I said, from the dilation of the different conversion levels. And we also have a reduction of 50% in the copper, which comes from the reduction of the cable length and the cable sections. So this dual benefit shows that the distribution in DC is not only energy efficient, but it also helps to reduce the pressure on some non-renewable resources like copper.
Okay, Mom, thank you. Then I'll take you to a trip to Berlin to Zone 1 demonstrator we set up there. And this application is not inside the building, it's outside the building, and it's about PV to vehicle. So it's a photovoltaic system used to charge vehicles. So if you look at the diagram on the left, we are relieving stress from the AC grid by directly connecting the PV system to DC. So it doesn't need to take the trip over AC conversion to get back into the DC grid, because most of the customers, like shopping malls or, as I said, bus depots or parking lots, small industry companies, they do have quite huge PV systems in the area of 400 to 800 kilowatts. And sometimes it's difficult to even get a grid connection for such a large PV system. That's the congestion type that we've seen in the beginning. So, but what you could get is a grid connection of half the connectivity. So for an 800 kilowatts installation, you just get 400 kilowatts. And because you have the DC connection, you can take off half of the load and directly feed it into the battery. And this is relieving stress from the power grid. And at the same time, you are economizing on converter losses because now the direct current goes directly to the battery and you take it from here to charge vehicles. So this is something we set up in Berlin. And here it's a zone 1 concept using conventional power converters for ILC, for interlink converters. So this one is using a voltage level of 700 volts. There was a question in the chat. The other one I've shown before is indeed using plus minus 700 volts. This level still remains in a low voltage area, the plus minus 700. It's one of the standard voltages of current OS, but of course, with the higher voltage, currents are much smaller and you have a bigger saving than on energy losses. So this is operational as a zone 1 concept. And if we go to the next slide, we also get the same amount of copper savings, which is a quite simple computation. On a DC system, you just need 2 cables, you just need 2 conductors. In comparison to the 3 conductors you would need for an AC system. So there's always 1/3 of copper savings. If you manage to increase the voltage a bit above the usual low voltage AC level, then the currents are getting still smaller and you are saving some extra copper. So that's the reason behind the copper savings. The reason behind the energy savings is, first of all, less converter losses. If you think of PV to vehicle, you take the power from the PV system, convert it to AC, convert it back to DC, put it to the battery, take it out of the battery to AC, put it back to DC to charge your car. Then you have 4 converter stages, which will cost you 12 to 16% of energy. That's just a waste of energy. The rest of the energy savings depend on the cable losses. And they are depending on cable length. So that's what we found out in terms of energy savings. And that's so far from me.
Wonderful, thank you. So this is Q&A time. Some of you ask questions in the chat. Maybe we'll start with those. Prashant, I let you go ahead with the question. And if you want to pick up with questions either in the chat or I see some hands raised, then we can go on. Prashant, over to you.
Yes, thank you, Raphael, and thank you everyone for joining us, and thank you, Stephan, Romain, and Mame for presenting. For the questions, I have the first question about the voltage level. There was a slide, I think slide 17, where or before, sorry, where there was a question about plus minus 700 voltage. Yes, this one. And the question was it's plus minus 350, so total 700 and not plus minus 700, right?
In the end, it's plus minus 700. Yeah. Because that way currents are getting much smaller.
Yes. Thank you, Stephan. And in fact, current OS specifies both plus minus 350, plus minus 700. You can always take the midpoint, yes, to come to the hub.
But I think the background of the question is that you need a special converter. And this is an isolating interlink converter. And I put it, you know, the AC plug you see below, the charging plug, works in the same way. So it contains a transformer. This is why it's isolating. It contains a transformer operated at a higher switching frequency. So the whole construction gets smaller. So that's the next generation of power converter that you will need to actually get to plus minus 700 volts. You can't do it from a regular low voltage AC converter. But I think there's a hand raised by Robert.
Yes, that's correct. My question is about the DC chargers. They are fed by DC on DC level. What is the highest power you can deliver at the moment with these hyperchargers? Is it like 90 kilowatt or 120 kilowatt or even higher?
They are modular, so each module can do 75 kilowatts, multiples of 75 kilowatts. What you can do.
Okay. And who's the supplier for that? Is that Schneider or is that one of the partners in the current OS network? Who is delivering?
In that case, it's MR. In that case, it's machine factor that we are doing. But you're right, because we didn't find anything, we developed it for ourselves. We are not intending to be a big supplier of charging stations, but we are looking for different suppliers to do current OS compatible products.
Okay. I have one more question on the chat. At what power levels are these? So I think, yes, Robert has already asked that. And one more, 20% of energy saving were based on the measurement of the installations. I think that was the last slide. Yeah.
Yeah, this one goes to Mame.
Yes, so to answer the questions, it was actually based on the measurement of the difference between the energy consumption of the installation before the installation of the DC demonstrator and after, so we get the 20% energy savings. So it was based on live measurement of the installation.
Thank you, Ma'am. There is also a question. Theo, you have raised your hand. So
yeah, sorry, I made a comment about plus minus 350 because there's plus 350 neutral, minus 350 totaling 700, right? I always understood that it's divided in 2 times 350, and of course, if you go from plus to minus, you get 700 then.
Yeah.
So yeah, it's not 2 times 700, right?
It is 2 times 700.
It
is. And we're using that in the charging stations already. So you do that by modular converters, dual active bridge converters. You can stack them into multiples of 700 volts.
Okay.
But you're right. You cannot do it with a conventional AC DC converter, low voltage converter. That's impossible.
Okay. Any other questions? I see, Robert, your hand is still up. Do you have another question?
Sorry, no, I took it away.
No worries. Okay. Don't be shy. Go ahead if you have more questions. Okay. I think you are very good in your presentation. So I think we have responded to the questions. In any case, if you have further questions, do not hesitate to connect to one of us and we can answer to your questions.
Sorry, I had one left. I saw you had the 350 volt DC outlets there. What devices are already suitable for 350 volt DC outlets? What can you connect to that? It was in the French.
Yeah. Go to the buildings from.
Yeah.
Rafael, can you change this slide to the one with the building?
Yes, let me go. This one here.
No, it was with the 3 pictures next to each other. You saw the outlets with a normal. Yes, sorry.
This one. Yes, sorry.
Yes.
No, the other one, but never mind.
There's an outlet. Sorry, I missed.
There's an outlet with USB-C, and there's an outlet, a large outlet with
this one
with 350 volt DC on it. Which device is already suitable to use that?
I didn't understand. Is this switchable too?
No, you see on the left, you see in the USB-C.
Yes.
And under that, you see a large DC output.
Yes.
And you mentioned that that's a 350 volt DC output, right?
It's this outlet is powered in a 630 volt, yes. Voltage
one
level.
is in USB-C and the other one is in USB-E. A.
Okay, but
So
what devices do you currently connect to the USB-E?
Yes, two sockets, one in USB-C, is the other one in USB-A.
Oh, it's for to charge phones or electronic devices.
Okay, then I misunderstood because I thought the large it's a USB-A, not a USB-E.
Yes.
Yes.
Okay.
Yes.
Okay. Sorry,
I
misunderstood.
The bottom of the picture is an USB-A, and the first one at the top is a USB-C.
Okay, clear. Thank you.
Okay. Good.
Rukia was asking a question. Rukia, go ahead with your question.
Hello, can you hear me?
Yes.
Yes. And no, it was just to complement on the comment. So I'm from DC System. We are the supplier of this USB actually. The input voltage supply is 350, but the output follow the USB protocol. So whatever device you connect, you can use either the USB-C port to charge your phone, but some other devices sometimes take the other form of the USB-A. So the output actually depend on the load you connect, but the output voltage is not 350.
No, understood.
Yeah.
Yeah. I understood that from the presentation. I was a bit confused, but that's clear. Thank you.
Thank you.
Okay, thank you, Rukia. Okay. Any more questions?
So I have one question to all of you attending here today. We are working on the next set of webinars of CurrentOS. So if you have any preferred topic that you would like us to present or develop in 2025, please go in the chat and tell us what types of DC topic is interesting or in a question for you today that CurrentOS could build a webinar on. Is it cyber security, or is it the reference document of CurrentOS, or what kind of topics would you like CurrentOS to have webinars about? We are eager to know.
Yes. Go ahead and mention in the chat if you wish.
I see the dots are moving at the screens.
Yes.
The screens are moving up.
So we could have a lot of topics. We could have questions. There are questions on voltages, so we can have a presentation on that. We can have presentation on the droops. We already had a webinar on droops, so you can go and have a look also on that. You can have a presentation of earthing systems. You can have presentation of the zones of defined by CurrentOS. So don't hesitate. If any topics interest you, you can put it in the chat.
No, nothing comes up. So that's it. Thank you for joining. Thank you to our hosts today, Stephan, Mame, and Romain, for being here with us, and to all of you who participated. We will share this webinar recording on LinkedIn, so if anyone couldn't attend and they can be interested, please share with them, and hope to see you soon. Have a great end of 2024 on your side, and see you soon in 2025.
Thank you, everyone.
Thank you.
Have a nice end of the year.
Thank you.
Bye-bye.
Thank you.